Thank you. I'm Kalin Kaskaval. I lead the compiler and tools team at Barefoot, obviously dealing with P4. And the first session is almost industrial, the industrial session. We have speakers from Google, Arista, and UW in collaboration with Microsoft Research. The first speakers will be Konstantin Weitz and Stefan Hoyle from Google, and they will be talking to us about using P4 for fixed function switches.
Today I'm going to talk about how we can leverage P4 for fixed function switches, as was already said. And this is joint work by Stefan Vakar, who is probably in the room as well. I've seen him before, right over there, and me. So you're all aware, I hope, how P4 works for programmable switches, right? You have your P4 program, and you use that and take a compiler and put it on the hardware, and then your hardware implements what your P4 program is supposed to do. And this works really well. The one problem is that not everyone has all these, programmable switches laying around. There's still a lot of fixed function switches that we need to continue to support. And the question is, can we use P4 and leverage that even for fixed function switches? Now, when you do that, first of all, the arrow is going to be somewhat reversed, right? You're going to have to design your P4 program to actually match what your fixed function can do and what you've been doing for years with your fixed function switches. So you're going to have to model L2, L3, all these crazy things that you have on your fixed function switch, right? But it's not quite like that. There's a bit of subtlety here, because you don't have to really literally model everything on the switch. You really only have to model what you use, and you can also model it on a bit of a higher level of abstraction. So for example, we skip any unused features that the switch provides in some roles that might be L2. Then you only use keys and actions that you actually use, right? You use table sizes for the flows that you're actually going to install. Like some of our tables in our P4 program have like 13 entries, right? Which is like a weird number. And then even fixed function switches, a lot of them still have like configurable aspects, right? And in that case, we don't model the configurability, we just model how we use it, right? And so it's kind of this synergistic thing where the hardware defines or influences our P4 program, but our use cases do as well. Now, the question is, why would you want to do this, right? You already have your fixed function switch, right? You can't really compile your P4 program to it, right? Or at least only for the configurable part, so why would you want to do it? And I think Nate said this pretty well, right? It provides a very clear contract. This P4 program specifies exactly what forwarding you want the switch to do. And this enables us to operate a heterogeneous fleet, right? If we don't care exactly how the hardware works, we just make sure it implements the P4 program, that makes it a lot easier to operate multiple switches. It also allows us to automatically generate some configuration. As I said, this is very similar to P4 switches that are fully programmable. And it enables switch validation, automated switch validation. And I'm going to talk in more detail about that now, because that's probably the most deep of these topics. So let me break it down. What does automated switch validation mean? So it's 3 words, automated. What that means is we don't manually write any test inputs. Instead, we generate them automatically. And we do that using production data and by analyzing our P4 programs. Now, the second word is switch. What does that mean? That means we're verifying a single switch. So these techniques that I'm describing, they're not for the whole network, just a single switch. And we're hoping if we hammer out this contract very clearly, it's going to be much easier to build a reliable network on top of that. And then lastly, we have validation. So the outputs from our actual switch, we need to actually make sure that they are correct, right? That they are what we expect them to be. And so we compare them to what a P4 simulator would actually do with the same state and the same packets that the switch is receiving. Right. Now let me give you a quick overview of what the rest of the talk will look like. So in the middle, we have the P4 switch that we're validating. We're validating two interfaces here. On the one side, the control plane. On the other side, the data plane. For the control plane, we validate through replaying production traces. And we also fuzz flows. And on the data plane, we do automated test packet generation. And Stefan is going to talk in more detail how we did all of this.
Thank you, Konstantin.
Yeah.
All right, so let's get started with the control plane testing, and in particular, fuzzing for the control plane. The idea of fuzzing is that you basically randomly generate inputs to your switch. In this case, we will randomly generate flows and groups that get programmed on the switch. And the key feature that you want your fuzzer to have is that it should generate inputs that are well-formed enough that they do something interesting on the switch. So for instance, if you just randomly generate inputs that are totally malformed, then the switch will just reject them and will not install them on the hardware. And so your testing is quite limited. But luckily, P4 tells us very precisely what these flows and groups need to look like for them to be valid. So we know exactly what kind of groups, we know exactly what kind of tables we have, what kind of fields we can match on, and what kind of actions we can use. And so that makes it pretty easy to have these well-formed inputs. And every now and then, we can also generate some invalid inputs to make sure the switch is reliable and rejects them appropriately. And so once we have a whole bunch of these flows and groups that we generated randomly, we send them to the switch, and the switch will respond in some way or another through P4 runtime. And we'll say, yes, I installed this flow correctly on the hardware, or I couldn't install this flow for this and this reason. And again, P4 gives us enough of a specification of what is supposed to happen that is pretty easy to tell whether the switch's behavior was correct in a given state. So for instance, if you have a well-formed input, then that needs to succeed if the entry is not already installed on the switch. With the only exception, if the switch runs out of resources, like the hardware resources, then it might reject the entry even if it's well-formed and not already installed. And that makes it very easy to test that the switch is doing the right thing for all of the flows that we randomly generate. Speaking of resource exhaustion, one thing that we find at Google that there's a lot of bugs around the resource exhaustion and sort of being close to the resource limits because switches have various bookkeeping that they need to do, and it's a pretty rich source of bugs. And our fuzzer can help a lot here. The way we wrote our fuzzer, it generates both insertion and deletion requests for flows, and it generates more insertions than it generates deletions. And so over time, as the fuzzer is running, the switch hardware is filling up, and eventually we run out of resources, and the switch will start rejecting some of the flows we try to install. And our test just checks that so as long as we're below the resource limit, the flows get accepted as appropriate, and afterwards the switch may reject flows. All right, now let's switch over to the data plane and how we test the data plane. The setup is as follows. We have our P4 switch at the bottom that we're trying to test. And then we can compare that with the P4 simulator, BMV2 in this case. And we start by installing a bunch of flows that we care about. This could either be from the fuzzer that we have, could also be from a production trace of flows that we actually care about. And then we just send packets to both of these switches. One is the actual switch in hardware, and the other one is the simulator. And we get two sets of output packets, and then we can compare whether they actually match. And now, obviously, the interesting part is how do you come up with the input packets? So we have a packet generator that takes the flows that we have and generates interesting packets. And when we say interesting here, what we want intuitively is we want to tickle like all of the interesting behavior in the switch, so sort of have as much coverage as we possibly can of the switching behavior. And one way to achieve that is with the following intuition. We try to hit every flow that is installed on the switch. So in this example on the slide, I have a very standard IPv4 longest prefix matching table. And there's some flow installed in that table, and we want to hit this flow. So we want to generate a packet that will be matched by this table entry. And so to do that, obviously, you need to make sure that at least the first 16 bits of the IP match this 10.152. And so we can sort of express that as a formula by saying like the destination IP needs to have this particular format. And we also need to have the VRF be precise, and I'll get back to that in a second. But even more so, we also need to make sure that actually we don't match anything that might shadow this entry that we already have installed with a longer prefix, because this is the longest prefix match. So if there's a longer prefix, like a /24, with the same first 16 bits, then that would obviously get matched. So we need to amend our formula by saying, like, we also need to avoid any other entries in this table that have a longer prefix. And now coming back to this VRF, the VRF is not actually a field of the packet itself, but this is something that is assigned earlier in the pipeline. So there's this thing called a VRF classifier table, where we match on a whole bunch of fields of the packet, and then we assign VRF as the action of that table. And so now we need to make sure that if we want to hit this IPv4 LPM flow, we need to have VRF 42. So we can pick any entry in the VRF classifier with that VRF and make sure that we match that entry. And again, we have to make sure that we don't match any of the other entries that might have higher priority in the VRF classifier table. And so what we end up with, sort of intuitively, is this formula that says like a Boolean formula over the bits in the packet. And we can use well-known techniques to solve these formulas. In particular, there's something called SAT solvers, which stands for Boolean satisfiability. And they are very efficient in solving these kinds of problems. And so what they will tell you is, first of all, whether there is a packet that can actually hit this particular flow. And then also they will give you an example of such a packet. And if you have done any work in sort of formal verification or using SAT solvers in other contexts. So for instance, if you try to analyze a C++ program, you might know that that actually is really difficult and sort of in general is very difficult to get right. And usually these automated approaches don't actually work all that well. But for the switches, it's actually quite different. For the switches, this works extremely well. And the reason for that is sort of twofold. The most important factor is everything is finite. There's no sort of unbounded structures. There's no looping, no recursion, no lists. And that's an extremely good match with these SAT solvers and SAT solving technology. And then, of course, it also helps to have the switch semantics be very rigorously defined by the P4 program, which allows us to sort of encode everything as a SAT formula. I also want to take a moment to contrast to OpenFlow and how P4 really enabled us to do this automated testing. So OpenFlow is what we used to use before we started working with P4 at Google. And P4 provides a very clear semantics, which allows us to have this extremely precise oracle. In particular, we have this simulator that basically precisely tells us what is the switch supposed to do. And on top of that, the semantics are also sort of simple enough that we can do all kinds of fancy tricks, like using these SAT solvers. And we can ask questions like, say I want a particular output packet, maybe an output packet that goes out a specific port. I can now ask a question like, what kind of input packet do I need to get that output packet? So it's almost like running the P4 program in reverse, which is pretty cool. So starting to wrap up, what kind of bugs did we find using these techniques? Obviously, one measure of success when you look at automated validation is like, did you actually find bugs that you care about? And we did. We found lots of bugs. We found bugs in the switch. And this isn't actually bugs in the forwarding, like in the forwarding ASIC, but in the software that's running on the switch. But we also found all kinds of bugs in the SDN controller. We found bugs in our P4 programs. So it turns out we didn't actually model all of the things the way we intended to. And we also found bugs in the simulator. So there's basically bugs everywhere. And it's kind of nice that these techniques really help you figure out like what part of your pipeline is wrong. And so in conclusion, I think P4 really enabled us to have this very clear contract of what the switch is supposed to do that allows us to run our heterogeneous fleet. It can help us automatically generate parts of the switch configuration, and we get a lot of traction by doing this automated switch validation. And I just want to close with, if any of this sounds interesting to you, we all work at Google. If you are interested in like applying these kinds of things, we're always hiring, so reach out.
Questions? You.
So one of the things that I thought was interesting that you didn't delve into very much is that you talked about using P4 to generate the config, or maybe like you talked about using the P4 runtime Azure
Yeah, absolutely. So from the P4 programs, you automatically can generate sort of the P4 runtime stub. But then obviously the implementation of how whatever the P4 runtime server on the switch, whatever that gets, and how you program the hardware, that you need to implement yourself. So there's not really anything that we do automatically at that point. But I mean, these fixed function switches, they still have certain parts that are configurable. And for that, you can automatically generate parts of the configuration, if that helps. We can also talk more offline in a bit more detail. Yeah, I think for the most part it's manual inspection because, like for instance, when the P4 program is wrong, it would be really difficult to automatically tell that that was the problem, right? Like really only a human can tell you that that was the problem. But for the most part, it hasn't been too bad to actually do this manually. When you when you get a discrepancy between what the simulator says and what the actual switch does, you can sort of look at the program and you look at the output packet or an input packet and think about like what do I actually want the switch to do, and it's relatively clear where the bug category goes. So that hasn't been too much work. So we haven't really spent any time like automating this process.
That said, I think one thing we could do is we have our old switches that still speak OpenFlow, and we could kind of translate P4 to OpenFlow and also run the same through our existing switches and make sure that at least we're implementing the same bugs that we implemented before. Right? We have other interfaces to the switch, right? Like you need to boot up the switch, you need to like configure LEDs to blink and stuff like that. There are definitely other APIs. Yeah, GNMI and GNOI are, if you're interested, you can look into those. Is that the question?
For the data plane.
Oh, for the data plane. So I had that question yesterday. So I think the P4 language itself is very good. Then there's also like the PSA and V1 model, right? That gives you like ingress and egress. And that works pretty well for some of our fixed function switches. But sometimes we hope we had more flexibility there. So if you guys want a challenge, come up with a way to quickly add like new kind of architecture models. I think that would be very helpful.
Any other questions?
I think they're in the back.
Okay. Vladimir.
Just wanted to ask you if you could describe what kind of functionality you were able to model so far and what you had to leave, and what were the challenges doing that?
I think we can basically model all our existing, I think we can model most of our existing use cases. And even if you can't model something precisely in P4, right? Even if you need to use like an extern or something, you can still control it through P4 runtime, right? You can still have like a virtual table, and maybe the semantics of your program isn't quite right, but you can still use like P4 runtime to program it. So I think in the end, you always have the escape hatch. You can always use like an extern or something until you figure out a better way by like, extending the architecture and things like that.
So maybe as a follow-up, specifically, say for the functionality of fixed function components, which are still part of the data plane, like multicast engine, for example, this functionality differs quite a bit between different vendors. So how did you model that?
I think part of it is that Google isn't all that crazy. Like we don't. Yeah, I don't know. I don't want to go into too much detail, but like I think a lot of it is that we model on kind of a high-level abstraction, right? And then I think also in the data center there are some of the challenges that you might face in other places we don't necessarily face. So some things are also easier for us, I think. Yeah.
All right.
Sorry.
You can take it later with
Yes.
Vladimir and sort it out.